So here's the first non-calculator question from the Bluebook test preview. This problem presents us with a graph of f prime, the derivative of a twice differentiable function on the closed interval 0 to 4. They say that the areas of the regions bounded by the graph of f prime in the x-axis from 0 to 1, 1 to 2, 2 to 3, 3 to 4 are these values respectively. The graph of f prime has horizontal tangents at 0.6, 1.6, 2.5, 3.5, and we know that f of 2 is equal to 5. Part A is asking us to determine on what open intervals in the interval 0 to 4 is the graph of f both decreasing and concave down. Give a reason for your answer. So I actually went with my reasoning up front. I know f of x is decreasing when f prime is less than 0. So what I did on this graph is I highlighted the stretches of the graph in yellow where f prime was less than 0, right? This is a graph of f prime. This graph is less than 0 when it's below the x-axis. I know that the function is concave down when the second derivative is negative. Well, if I'm doing this with a graph of f prime, I know that the slope of f prime is what tells me the value of f double prime. So when I have negative slope on this graph, or when f prime is decreasing, I know that my function f is concave down. When you give reasoning statements like I've done here, just be very specific. Don't use the word it. Don't say the graph. Reference the function, the derivative, the appropriate derivative. Little details like that can make or break your give a reason for your answer point. Now, on this graph, I highlighted in green the stretches where I see f prime, so the graph that's actually here, f prime decreasing on that stretch and on that stretch. Where do I see overlapping highlights of both green and yellow? That would be from this location down to the bottom of that little portion of the graph, and then from this x-intercept down to the minimum, the local minimum on that stretch of the graph. So that's pretty obviously 1. This location right here, they actually tell us, is 1.6. This location pretty obviously is 3. And then this location down at the bottom here, they also tell us that as 3.5. They do ask us for open intervals. Open intervals do not include endpoints, so make sure when you give your conclusion, you don't have your endpoints being included. Part B asks us to find the absolute minimum value of f on the interval 0 to 4. Justify your answer. So when you're looking for an absolute minimum of a function, you need to know the candidates where that absolute minimum might occur. That would be endpoints of the interval. Endpoints of the interval are 0 and 4, and locations where the derivative of what you're trying to optimize is equal to 0 or undefined. We don't have the undefined portion apply to us here. This derivative is always defined. But when is f prime equal to 0? Actually, quite a bit. It's equal to 0 at the endpoint, there, there, and there. So we actually have 5 locations where the absolute minimum might potentially happen on this interval. Now, what I did is I recognized that f of 2 is 5. So right away, if I have these as the candidates where the the minimum might be, I want to know what my function value for f is at each of those locations. I felt it was going to be easiest to kind of start in the middle of the list at 2 because I already know that answer. At 2, my function value is 5. Now, if I know the function value at 2 is 5, and I want to figure out what the function value is at 3, what I'm going to need to do is I'm going to need to integrate the rate of change of the function, which is the derivative, from the time that I know the function value, which is at 5, to the time that I want the function value, which is at 3. So how are you going to find this integral value here? Well, that's why they provided you with all these area arguments. On the interval 2 to 3, this area that you see right here is 10 square units. Because that area is above the x-axis, this integral is going to have a positive value, which means my function value is going to rise by 10 units from 5 up to 15 on the interval 2 to 3. I'm going to then do the calculation to get f of 4. I already know that f of 3 is 15. I now need to add on how much the function value changes by from the time that I know it, which is at 3, to the time that I want it, which is at 4, by integrating the rate at which the function value changes. So again, how do I find the value of this integral? Well, I have to use area arguments. They tell me that that last little portion between the graph and the x-axis has an area of 14 square units. Now what you do have to realize here is that that region is entirely below the x-axis, so my function value is actually going to decrease by 14 units from the x value of 3 to the x value of 4. So 15 minus the 14 takes me down to a y value of 1. Working backward is a little bit trickier. I know the function value at 2 is 5. I'm going to add on how much the function value changes by from the time that I know it to the time that I want it, which on this line is 1, by integrating the rate at which the function changes. Now these limits of integration are not in the right numerical order. I can negate the integral and flip the limits of integration in order to use signed area arguments the way that we've developed for them to work over the course of your calculus course. So I have changed this operation from addition to subtraction, and that would mean my integral then goes from 1 to 2. Well, from 1 to 2, my 6 square units sit below the x-axis, so I'm subtracting that off. Well, subtracting the negative ends up giving me a result of positive 11. And if I go back to 0 from that positive 11, I am adding on how much the function value changes by from the time that I know the function value, which in this calculation is at 1, to the time that I want it. Again, the limits of integration are not in the proper numerical order to make signed area arguments work the way I want them to, so I've changed the operation from addition to subtraction. And I have not negated the integral here because that integral value is for a region that's across a stretch where the graph is entirely positive. So my lowest possible function value for f looks like it's this final one at 4. So the absolute minimum of f on the interval 0 to 4 is 1. There are a couple other ways you could potentially justify this. I think this is probably the most foolproof one that works in the widest variety of scenarios, which is why it's the one that I've presented. Part C, evaluate the integral from 0 to 4 of f of x times f prime of x with respect to x. So what catches my eye about the formation of this integral is that it involves a product. And a product within an integral is always going to be an issue. And in Calc AB, now in BC you have some other options, but in Calc AB, the primary way that we've handled that is to do a u-substitution. If I let u equal f of x, the derivative of u with respect to x is f prime of x. If I solve this equation for dx, du over f prime of x is going to replace the dx. As I do my work within an FRQ when I'm carrying out a u-substitution, I am in need of making sure my notation flows appropriately, meaning my limits of integration are needing to change from the x values that they start as, 0 and 4, to the corresponding values of u. So what is u of 4? Well, f of 4 is u of 4. That's something we can take from the table back here. F of 4 is 1. Similarly, also from that table, u of 0 is 9, right? So my limits of integration change from 0 to 4 to 9 and 1. I substitute du over f prime of x in place of the dx. These are going to undo one another. I'm then left with just u with respect to u on the interval 9 to 1. I do my antiderivative, so add 1 to the exponent, divide by the new exponent. When you adjust these limits of integration from the x's they start as to the corresponding u's, you do not need to back substitute, right? So I'm literally putting 1 in place of the u, I'm putting 9 in place of the u. This line right here would receive full credit, even if I had like 1 squared in this numerator and 9 squared in this numerator, I'm good. Scoring guidelines for this would say -40. You don't have to simplify to this. An answer like that in a non-calculator FRQ, calculator FRQ even, is totally okay. Last part of this says, hey, here's a function g of x, x cubed times f of x, find g prime of 2, show the work that leads to your answer. So you hopefully look at this and realize if you need to find g prime of x, I'm going to need to use a product rule. So derivative of the first piece of the product, original second, plus original first times derivative of the second. I now need to put 2 in place of all my x's. This line right here will not receive full credit. This line right here depends on f of 2 and f prime of 2. I'm in need of putting the value of f of 2 and the value of f prime of 2 into this appropriately. So f of 2 was provided to us. F of 2 is 5, so I've replaced f of 2 with 5. F prime of 2 I can get from the graph. On this graph, the derivative's value, since it is a graph of the derivative, is 0. This line right here would receive full credit. If you do simplify that, you do get 60, but you take on a little extra risk, waste a little extra time if you try to take it to this end result.